All right. Today is the 1st, September 1st. All right, so I'll go over one of the problems that a student asked me for. So this is homework number 1. We can do some here. And I want to go over number 11. Okay. So number 11 says we have a standard deck of cards that consists of 4 suits, right? So we know what a standard deck of cards is, I hope. And we know that there's 4 suits. There's clubs, diamonds, hearts, and spades. And each suit has 13 cards. We have ace, 2, 3, right? So we have hearts, we have diamonds, we have clubs, and we have spade. Right? These are our 4 suits. And of course, we have 13 for each of them, right? We have 13 cards, 13. So that makes for 52 cards. And we have these cards go from ace to all the way to 10. Then we have jack, queen, and king. And this goes for all of them, right? And then we want to figure out how many. Well, I may have a different number than some of you guys. So they sometimes some of the questions have a randomized version of them. So I want to know how many 7 card hands have. Mine says exactly 4 hearts and 2 clubs. So I want exactly 4 hearts and 2 clubs. Does anybody have any idea of how to begin this? Has anyone been able to solve this one, or has anyone yeah, has anyone thought about this one? So we want 4 hearts. How do we get, what are the number of ways to get 4 hearts? Yeah, you do lose a card in the deck. Okay, so 13C4. Yeah. This question deals with combinations. I know we briefly went over that at the end of the last lecture. So you haven't seen it in its full application mode yet, but this terminology, 7 card hand, right? You know, we talk about that a lot in like card games, particularly poker. I don't even know how to play poker, but I know you need a hand, right? And so a hand is just a collection of cards. So you have 52 cards and you want to choose, and you have a hand that consists of 7 of those cards. And 7 of those cards, you want 4 of them to be hearts and you want 2 of them to be clubs. So hearts and clubs, right? So I want them to be hearts and I want them two of them to be clubs. And so the question is, how many cards, hands are there? Well, first we can break it down. How many ways can we select 4 hearts? And I think Daisy said it, right? 13C4. Does everybody see that? So the number of ways to select 4 hearts. So 4 hearts out of 52 cards, right? Is simply 13. I know people write this, right? 13C4. I'm also going to write it using the binomial coefficient notation. 13, choose 4. Okay? I want to just make sure that you guys are saying there's another, this is the way we usually pronounce it. We say 13, choose 4. We choose 4. And we know how to compute this, right? We do what? 13 factorial over 4 factorial times 9 factorial. And we can use a calculator for this. I just want to make sure we know how to break this down by hand as well, because that's also a good way to do so. So I'm going to break it down. 13 factorial on the top. I'm going to write it as 13 times 12 times 11 times 10 times 9 factorial. And I do that because there's a 9 factorial in the denominator that I can cancel out. So I can cancel these out. And then I'm left with 13 times 12 times 11 times 10 divided by 4 times 3 times 2 times 1. So the 3 times the 4 goes into the 12, right? So they divide. Do you see how we can divide that? 4 times 3 is 12. So I divide the 12 out. And the 2 here divides, and I get a 5, right? So really the product is 13 times 11 times 5. And if you multiply that out, 13 times 11 times 5, I get 715. There's 715 ways. To do what? We have 715 ways to select 4 cards that are hearts out of 52, right? Well, there's only 13 hearts to choose from. That's why we only do 13C4 or 13 choose 4. Because to get hearts, there's only 13 of them. I want 4 of them. Which 4 of them? I don't know, but I want 4 of them. And do I care about the ordering of those cards? I don't. I just care about getting 4 of them. That's why 13 choose 4 is used. Combinations are used. Okay, so I know that one thing, right? So that helps. Now, the same question arises, right? Well, if I took care of the 4 hearts, how about the 2 clubs? How many ways can I select 2 clubs? And then now people start to see, okay, so from here we can say what? 13, choose 2. Or 13, choose 2, right? And so we do the same thing again. We can compute this, 13 factorial over 2 factorial times 11 factorial. This is 13 times 12 times 11 factorial over 2 times 11 factorial. The 11 factorials cancel. And I'm left with 13 times 12 over 2. The 2 goes into the 12 6 times. 13 times 6 is 78, right? So far, so good.
How I get how we get 4 out of 13 and 2 out of 13, but if I but it's from a stack of 52 cards, shouldn't I first make sure that I'm getting any hearts out of the 52 cards?
Say that one more time.
If I have a stack of 52 cards and choose 4 cards at random, I can get 4 cards, but not four hearts out of 52 cards. Shouldn't it be 50? 4 choose 1 times 4 choose 13. 13 choose 4, because 4 choose 1 to make sure that we get the hearts.
4 choose 1.
Yeah, because I have 4 different types of cards.
Before choose 1, you're saying I have 4 things. I choose just one of them.
Yeah, I have 4 types of cards and I need to get hearts.
Okay, so you're saying 4 choose 1 first, and then 13 choose 4. Is that what you're saying?
Yeah, because 13 choose 4 is just 4 cards out of a total of 13 hearts. But how do I know that I'm getting hearts?
And then you would say 4 choose 1 as well for 13 choose 2.
Yeah, because I need to make sure that I'm getting clubs.
I see what you're saying. So you're making the selection of the choice of hearts first. That's what you're saying?
Yeah.
I see. Yeah, we may have to account for that as well. Um, yeah, sometimes the counting can be quite an undertaking. So let's see. So if you say 4 choose 1 first, and then we select the out of the hearts, we select the out of the hearts, which are 13 of them, we select 4 of them. That'll be 715 ways. And then, but there's something about that. So we'll get to that. We'll get to that. But once you find the ways to select, if you do select the hearts, the deck of hearts, right? Let's say we separate the 52 cards into stacks. Is that what you're doing? So sometimes there's different ways to count it, right? So I think what you're doing is it's not completely, no, the order doesn't matter here. It's not completely random then, Mir, right? Like the way you're counting, it's like you're distributing the or you're organizing the 52 card deck into stacks of 4 different
Right.
piles.
So
And
so
each,
then so
uh-huh.
then we have to multiply the 13 choose 4 times the probability of choosing 4 hearts to begin with.
Well, be careful. We haven't even talked about probability yet.
But
So
what's the number of ways I can get 4 hearts? Oh, if it's not probability, then it does make sense.
this is just counting. The next order would be a probability question, which is how many. What's the probability of giving a, like the question would be, well, what is the probability of getting a 7 card hand that are exactly 4 hearts and 2 clubs? Then you would have to compute the number of ways to get a 7 card hand, just a random one. So we're not even in the probability world yet. We're just learning how to count a little bit, you know. But the way you're considering it is this: you're saying, okay, I have 52 cards, and you separated them in your head already, or physically, into piles of 4 different suits. And then you say, I want to count the ways to select hearts.
I mean, no, I didn't separate them in my head. I just have to think about, if I choose 4 cards at random out of the 52 cards, how do I, okay, 4 out of 13. If I know that I'm gonna get hearts, then 13 choose 4 is good. But if I don't know that I'm going to get hearts because I'm choosing them at random, then the number of ways to select four hearts out of.
I see what you're saying. Um,
Actually, no, I'm so confused. I'm sorry.
no, no, it's okay. The thing is, I know what you're thinking already about randomization, random selection, which is good. The thing is, in this problem, we're specifically told already what we're expecting. We're not considering the possibility of not getting a four hearts and two clubs. We're considering the only possibility that this is what we want.
Got it.
So I just care about what we want. I don't care about what could not occur, or like I'm not considering all possibilities. I'm not considering that yet. I'm just considering, hey, if I have 7 cards, how many different hands have 4 hearts and 2 clubs in it? That's all I'm considering.
That makes sense.
Okay.
I apologize for it.
No, it's okay. So I guess what don't apologize. I guess if you do want to consider all realms of possibilities for 7 cards, so how many 7 card hands? Let's do that first, okay? Before we continue with this, let's just make a little like a side note here. And it's just to give us maybe more understanding of what probability will eventually entail. And if it would eventually entail finding all different ways for something to occur. So why don't we consider that? How many ways are there? How many total ways? How many total 7 card hands exist or are there? Of course, out of 52 cards. So if I had just had to enumerate all the possibilities of having just 7 cards without any restriction, it would be what? 52, choose C, 52 C, 52 choose 7, right? Or 52 choose 7 like this. Now, of course, this number is pretty big. I will not be able to compute it by hand myself. For those of you who have calculators, I don't know if you guys know that you can use a calculator. If you have a TI-84, I'm going to be using an emulator here to show you how to compute this stuff. So let me share my new share. So do you guys see it? The calculator? So if you guys have this calculator TI-84, you can utilize one of the functions here. And if you go to math, and then you go to PROB, which stands for probability, you can use several things that you've seen already. You've seen permutations, you've seen combinations, and you've seen factorial. So we're going to use combinations. So the combination here is 52 because I have 52 cards. And I just want to select 7 of them. I don't care what they are. I just want to select 7 of them. And when I do that, I get this number. I get what I get. I get 1, 3, 3, 7, 8, 4, 5, 6, 0. I get 133,784,560 hands. That's how many 7-card hands exist. So out of this 133,784,560 different 7-card hands, I want to know how many of these have exactly 4 hearts and 2 clubs in them. So I want exactly 4 hearts. Well, how many ways can I select 4 hearts out of 13 hearts that I have? And there's 715 ways for that. How many ways can I select 2 clubs out of the 13 clubs? And then the question is, what happens? It's a 7-card hand, isn't it? I'm including hearts and clubs. And so what happens after this? So if I selected 4 hearts and then I selected 2 clubs, that's only 6 cards. I need 1 more. So then, since they can't be, since there can only be 4 hearts and 2 clubs, and there isn't any more hearts or any more clubs, I have to select one of the other suits, right? I would have to select either a diamond or a spade for my last card. So then how many ways is that possible? So number of ways. So this is number 3, right? So we talked about the total number of hands, which is 133 million, which is a lot. And then it's okay, Mir. And then it's how many ways, number of ways to select one card that is not a club nor a heart. So how many ways is that? And I think someone said, right, 26. Choose one. I have 26 cards that are not clubs nor hearts, which happens to be diamond and spade. And I want to choose only one of them. And 26 choose one is like saying I have 26 things. I just want to choose one of them. How many ways is that? No, Alexandra, we're not considering pulling an extra heart or club for a 7th card, because if we do, suppose we do, then let's say we have one more heart, then that means that we would have exactly 5 hearts and not 4 hearts. And then if we have one more club, it will have 3 clubs instead of 2 clubs. So we can't have any more clubs we're choosing or hearts. We have to choose diamond or spade, and there's a total of 26 of them. Yeah, yes, so this word exactly is a very strong word. It's not like roughly, it's not approximately, it's exactly. So it's no more nor no less. Okay, so then there's 26 ways to do that, right? That's a quick one, 26 ways. Okay, and so then after that, what do we do? Can you give an example with the actual cards? I don't have a standard deck with me. So one thing about probability and counting, right? How counting is essential for probability. When we start learning about probability, well, to really just briefly mention the history of probability, right? It came out in like this theory of probability came out around the Renaissance time in Italy. There's a lot of Italian mathematicians that are named a lot that started this whole probability, like the Bernoulli brothers are one of them. You're gonna hear the word Bernoulli a lot. Bernoulli is Bernoulli. So Bernoulli is gonna appear again, and a lot of these probability basically came up in card games or in gambling. People were gambling and they wanted to figure out in a more quantitative fashion how is it possible to win, or what's the likelihood of winning or losing. So that's where it came up, and that's why a lot of our problems, what you'll see, deal with dice. Not just because dice are random, but it's because they use dice to figure out certain techniques and strategies to win. So they use dice, they use cards. um, what else do you use? Yeah, they use those 2 examples a lot. So you don't actually need to know how to play poker, or we're not playing a card game. You just do need to know the breakdown of the cards. Yeah, you just have to know that a 52 card deck, there's 52 cards, and they're separated into groups of 4, and one group are hearts. They're all hearts. It's like 4 different teams. So one team is heart, one team is diamond, one's club, and one is spade. And then for each of those teams, there's 13 members in each team. There's 13 cards in each team, and they happen to all be the same kind of thing. They contain an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, a king, and a queen. And there's that version for the hearts. There's also that for diamonds, and so on and so forth. So that's all we're doing here. Okay. And so then with these numbers that we found, what do we do with these numbers? Yeah, we should multiply them because we're considering each of these situations as an event, right? We're selecting 4 hearts because that's exactly what I want. I want 4 hearts out of the 52. And that's, it's not just a random, it's not a random selection of them. I want 4 of them to be hearts. So there's only 13 to choose from. So I select 4 of those 13, and there's 715 ways. I also want 2 clubs. There's only 13 to choose from. So 13 choose 2. That's how many ways I can get 2 clubs. And then the leftovers, there's only 26 leftovers that I can choose from. So I do 26. So when I multiply these out, these are the total number of ways. So I do what? 715 times 78 times 26, which is which is 1450020, and that is, there's a million ways. There's 1,450,020 ways to have a 7-card hand, and this card, this hand contains exactly 4 hearts, 2 clubs, and then the other card has to either be a diamond or a spade. Does that make sense? Can you quickly go over again when we would be adding them if we're dealing with an and or statement? With an or statement. Yes. So yeah, so see, counting becomes very dependent upon the wording, right? So the wording, so one thing I say to students is mathematics is probably the most, just of course I'm teaching math, so I'm going to be saying this. Mathematics is the most important subject to learn, right? Because that's what I teach. But then I say English is even more important. And why I say that is because, we need language, right? We're using language to connect ideas, to express our ideas. And mathematics is very precise, for the most part, at least what we're learning here, especially. It's a precise endeavor that we tend to do. So our wording is extremely precise. How many 7-card hands have exactly 4 hands and 2 clubs? And so this word and, right? Actually, it's not just any word and. We use and all the time, and so we don't really think much of it. But in mathematics, words like exactly, words like and implicate certain operations. So exactly, I can't have more than 4 hearts, and I can't have less than 4 hearts, and I can't have more than 2 clubs, and I can't have less than 2 clubs. I have exactly only 4 hearts and 2 clubs. Now, why am I not adding them? Why am I multiplying? So whenever you see this and, it tends to imply multiplication. But then think about why. Normally, when you guys are taught this earlier in your academic careers, if you talked about probability before in high school and stuff, They usually say and you multiply and then or you add, and they just leave it at that. But if you understand the fundamental counting principle, you'll see why we multiply. It's because we are trying to figure out the number of ways of something occurring together. That's where the and is, right? We want 4 hearts together with 2 clubs. So you can consider this as one event, the selection of hearts as one event, and the selection of clubs as the second event. So therefore, how many ways do we do one thing? And then how many ways do we do the other thing? And. But it's not because we're not multiplying because it says and, we're multiplying because this exact um, this result that we want occurs due to 2 different selections, one being hearts, the other one being clubs. So then it's natural to choose to apply the fundamental counting principle, which is multiplication of one event times the other event. Now, the or is when you're considering 2 mutually exclusive, and this word we're going to talk about later, mutually exclusive events, meaning that if one event occurs, the other one doesn't. This is not the case here. If I'm selecting 4 hearts, I'm not saying I want to know what happens if I don't select 4 hearts and select 2 clubs. If I do or, then this problem is completely different. The moment I change this and to an or, I'm saying something completely different. I'm saying I can have a 7-card hand and I have 4 hearts in them, and that's all I care about. And then you do or, I have a 7-card hand that has only 2 clubs in them. When you put that as a or, then this problem is the answer to that problem will be completely different. I hope that makes sense. Okay, so for now, I know people think of and just think of multiplication, but think more about the actual scenario that you're dealing with. You're dealing with 2 events combined into one, right? This is the 7-card hand, and I want something to happen, and I want another thing to happen as well. So then we multiply the number of ways. So of course, some of you may have different numbers. Like you may have I don't know, 3 clubs or 3 hearts, but the idea, the way in which you solve this problem is exactly the same. Okay, so I think I went a little too long with this. Is there any other questions that maybe I can solve? I feel like we should have a separate problem session for these type of things, because you need to be able to do these, and you have to be able to see them and how it works. So any other questions about this problem, about any other problem? Oh yeah. Okay, so I'll do that. I'll do that one, then we can move on. And I think what number is that one? I have a penny. That's number 1, right? Yeah, guys, number 1 is not as bad as it seems, and I know it's a weird question though. Yeah, it doesn't matter, right? So it says you have a penny, right? You have a penny, you have a dime, you have a nickel, and then they just start trying to be funny, right? A toonie, a loony. And so then, of course, these are fictitious coins. No one has a toonie or a loony. They don't make sense, right? But it's just for the sake of the problem. And so a penny, what do we know? A penny is what? 1 cent, right? We know a dime is what? 10 cents. We know nickel is what? 5 cents. What's a toonie and what's a loony? I don't know. Nor does it matter. A toonie is $2 Canadian. Oh, a townie. I didn't know that. But we can make it up. We can make up a toonie. A toonie is what? 2 cents. Let's just make that up. And then a loony is 7 cents. The assumption you had to make though is that a toonie and a loony, whatever that is distinct from a penny, a dime, and a nickel. Like they're different values, numerical values. So the question is, how many ways, how many non-zero sums are there? And the key word here is actually the what's in parentheses, non-zero. And if you look at it from this perspective, if you look at it from the perspective that I'll show you, hopefully it makes a bit more sense. So I'm giving you 5 slots, and why am I doing 5 slots? Every slot is for a one of the coins. So I got a penny, I have a dime, I have a nickel, I have a toonie, and I have a loonie. Now the question is, I can either have a penny. So in my sum of money, right? Basically, what they're saying, what are they saying? They're saying that of these 5 coins, how many different ways can I select them to create a certain number, right? So like I have 5 coins, I can select one coin only. If I select one coin, I can either select one penny. That's a sum of 1 cent. I can select one dime. That's 10 cents. I can select one nickel. I have 5 cents, so on and so forth, right? So selecting one coin, I have 5 different 5 different sums of money. Now, what if I select 2 coins? I can have a penny or a dime. 1 plus 10 is 11. I can have a penny or a nickel. 1 plus 5 is 6. I can have a penny or a toonie. 1 plus 2 is 3. So already I'm starting to create more sums of money. That's if I select 2 coins. And then if I select 3 coins, I can have a penny, dime, and a nickel. That's 1 plus 10 plus 5, that's 16. And I can have a dime, nickel, or a toonie. That's 10 plus 5, that's 2 plus 2, that's 17 cents. Do you start to see that? I'm just trying to figure out how many ways can I group them to produce a certain amount of money. How many different ways how many different versions of that occurs? I can select 4 coins, and then I can select the penny, dime, nickel, and a toonie. I add those up. What's the result? And then lastly, I can select all 5 coins. So 1 plus 10 plus 5 plus 2 plus 7. When you add that up, that gives you a certain amount. I want to count how many ways can I do, how many different ways can I produce a certain sum. Now, if I were to do exactly what I just told you to do, it would take a long time. And we don't have time for that. So that's why sometimes when Mira brought that comment up for the previous question, it depends upon how sometimes you envision or see the problem yourself. So one way is saying, okay, I select one coin. How many different results are there? I select 2 coins. How many different ways are there? I select 3 coins. How many different results are there? I can do that. It just takes a little bit more time. Sometimes there's a simpler way. And the simpler way is this. If you notice, for each of those scenarios of selecting one penny or selecting one coin or selecting 2 coins or selecting 3 coins, right? You can also think of it as in that selection of coins, which coins are in the group and which coins are not in the group. So in essence, what you can count is how many ways, or you can count what are the possibilities of having a penny in my group. So I can either have a penny in my group or I can have a penny not in my group. So that's a total of 2 possibilities. I can have a dime in the group or I cannot have it in the group. Those are 2 different events. That's another 2. I can have a nickel in my group or I don't select the nickel. That's 2 different ways of it occurring for the nickel. And so on and so forth for the toonie and for the loonie. When I multiply 2 times 2 times 2 times, that's 2 to the 5th power, that's 35, that's 32. There's 32 ways for what? There's 32 ways of having a penny, dime, nickel, toonie, loonie being either selected or not selected in my sum. But what we do is we subtract by 1. And why do we subtract by 1? because in this number of possibilities, if I were just to consider the 32 ways, one of those ways, right? One of those ways is if I don't have a penny, I don't have a nickel, I don't have a nickel, dime, I don't have a toonie, and I don't have a loonie. In that way, if I don't select any of those coins, I have zero money. That's why I have to subtract one from those 32, because one represents the zero sum. It represents the sum of zero. So if I take that away, I'm left with non-zero sums. And that's how counting can be a little strange, right? Because we don't necessarily care. We don't care about what the sums of money are particularly. We don't care about that. We just care to know how many of them are there. And that's the name of the game here. How many of them are there? That's all we really care about. Does that make sense? So the toonie, the loonie, they're just made of fictitious coins. It could have been called anything. Any questions about this one? No? Does that make sense now? I hope I didn't lose you guys with the loonie and the toonies. Okay. All right. So I'm gonna briefly continue. If there's no other questions, I know, Alexandra, you said number 19 was hard. You have a baseball league with 7 teams. This is at least my number. 7 teams and 9 games. How many games are needed to complete the schedule if each team plays 9 games with each other? I don't know. Your numbers may be different. I have 9 and 9. Oh, okay, I have 7 and 9. Okay, let's look at this one. This is number 19. So you have, I'm going to use mine, right? 7 teams. And each team plays with one another. Nine times. I didn't understand the language. Like each team have to play each of the other 8 teams 9 times each. That is what I interpreted as well. Right. So it says there's 7 teams, right? At least for me, or yours is 9, right? So what I'm gonna do sometimes, what helps a lot is drawing things out. So I have 7, right? I have 7 stars representing teams. Now, this guy here is gonna play this person, this person, this team, this team, this team, and this team. Right? Okay. And they play each other 9 times. So if I call this, let's say team A, right? If I call this A, B, C, D, E, F, G. In essence, this problem is asking how many connections can be made among 7 teams. So what do you notice? The first team plays 6 times, right? Six different teams because it can't play itself. And then, right, the same thing goes for what? For B. B plays A, but it also plays G, it also plays F, it also plays E, it also plays D, and it also plays C. and so on and so forth. Do you see the connections we're making? C is already playing with A, C is already playing with B, but C also plays what? D, E, F, and G. D is already has played with C and with B with A, but D also plays with E, plays with F, plays with G. And of course, this is an ugly drawing, but do you see the connection? E has played with A, B, C, and D, but also plays with F and plays with G, and finally G plays with F. So what I would do, and this is a typical counting problem, is count the number of connections that can be made. What are the total number of connections that can be created, established between 7 different objects? In this case, it's teams. In other words, how many different pairs can be created out of 7 teams? That's the first question. So what's the total number of pairs created out of 7 teams? Because to play a game, I need 2 teams. So Mir, it's not 2 to the 7th. Be careful with that. That's counting something else. But Rizwan, it is 7 choose 2, because what am I doing? I got 7 things and I want to connect 2 of them together. I want to pair 2 of them together. Pairing 2 of them together is like saying, hey, I have 7 things. I just want to make a group of 2. Do I care what the order is? No, I just care about having a group of a size 2. So 7 choose 2 is the correct answer. And you do 7 factorial over 5 factorial, 2 factorial. This becomes 7 times 6 times 5 factorial over 5 factorial times 2 factorial. 5 factorials cancel, and I'm left with 7 times 6 over 2, which is 42 over 2, which is 21 ways. Okay. So there's 21 ways. So when you count all of these up, if you were to count all of these up, there should be 21 connections. So once you establish a connection, right, A and B, how many games are played? 9. So then what do? You multiply by 9. For every connection, there's 9 games. So you multiply 21 by 9. 21 by 9. You get 189 games. Does that make sense? So I know I took some time, guys, but this is worthwhile. It's worthwhile because you start to see how to think. The most important thing is how to think. I know you want to know how to do it, but you have to learn how to think things out. And it takes some time to think it out. These problems sometimes require a little bit more thought as to why we do something, how to do something. You understand? So drawing things out like this helps. It does help. Because then once you start to visualize things, you start to organize your thoughts. And when you can organize them, you can maybe apply certain mathematical operations that help you find what you want. Okay. Okay. So I think we're good with this, right? So homework is due tonight. If you have more questions about a particular question in the homework, you can email me and I'll try to get back to you as quickly as possible. All right. Any other questions, comments? So yes, someone mentioned if I was gonna do anything new today. Well, I hope so. I hope we, the time we have left, I can continue with where I left off, which was on combinations, and then I talked about Pascal's triangle, right? Binomial coefficients. So we talked about combinations, and we figured out that combinations, right, is a way of counting the number of groups of a certain size that's selected out of a certain group, certain number of things. So the wording is n choose r. So we have n things, and I want to select r of them. And how many groups of r, size r, are there that can be created out of n groups, n things. So this combination tells us how many groups are there of size R. This is a formula that we talked about last time with factorials. And then I left off on this thing, right? The binomial coefficients. And what I want to do is I want to make the connection with Pascal's triangle. So just briefly again, Pascal's triangle is a triangle that emanates from starts from the top. We have one in the beginning, then we have another row. So you can think of these as rows, right? And each row gets bigger, more entries in them, but it continues to grow in a triangular fashion. So the ones here extend here. So all the ones are on the outside of this triangle. And then the numbers inside come from the previous two numbers when you add them up. So when you add 1 and 1, you get 2, right? So this number here is 2, and it comes from the previous two numbers here. So I'm just going to be the arrows that you see are not really typical in the Pascal's triangle. You just write the numbers out. But I just want to see, I just want you to see the flow of how the numbers come. And so then the next one here, I get 1, and then these numbers here, right? So these ones here continue all the way along the diagonal. And then I can combine the previous two numbers, and I get 3, and I get 3. And then this goes on forever. This goes on forever. So in essence, you can find every single row if you just continue applying this relationship, this recursive relationship. So we get 1, we get 4, 6, 4, 1, and so on and so forth, right? I'm not going to draw this all out, but now I hope you guys get the idea of what's going to happen every single time. And then what we saw was, for example, in this row, right? In this row, it's connected to the binomial coefficients because 3 choose 0 is 1. 3 choose 1 is 3. 3 choose 2 is 3. And 3 choose 3 is 1. So this third row are the binomial coefficients when you have 3 objects and you're selecting 0 of them. You have 3 objects, you're selecting 1 of them. You have 3 objects, you're selecting 2 of them. You have 3 objects, and you're selecting 3 of them. That's this number, that's these numbers here. And then when you go to the next number here, these are all when you have four objects. So 4 choose 1 is the same idea. 4 choose 0, there's only one way of selecting nothing. 4 choose 1, there's 4 ways to select one thing. 4 choose 2, there's 6 ways to do that. 4 choose 3, there's 4 ways to do that. And 4 choose 4, there's 1 way to do that. And what you should start to see is that there's a kind of symmetry. And so this is one of the combinatorial identities. There's a symmetry behind this. So note that there's a symmetry in Pascal's triangle related to binomial coefficients. If I have n objects and I select r of them, that's the same as saying n objects and leaving, in your selection of r things, how many things are left? If I select r things out of n things, I know I'm using letters a lot, how many things are not chosen? N minus r, right? So doesn't it make sense that the number of ways to select r things out of n things is equivalent to saying how many ways out of the n things do I not select n minus r things? Or out of the n things, how many ways is it to leave n minus r things out? So that's why there's this connection. That's why there's this symmetry. So if I say, hey, if I select one thing out of 4 things, there's 4 ways. It's the same thing as saying I have 4 things and I want to leave out 3. it's the same, right? It's equivalent. And these numbers here, that's why there's this pairing, there's this matching of these numbers. And the same thing goes for the next line, right? The next row. This is 1, 5, 10, 10, 5, 1. And then there's something briefly that I want to talk about called the binomial theorem. And we're not going to go so deep into this, but the idea is this. The idea is that now you can apply this reasoning. Let's say if you have like x plus y, right? If I square this, if I do x plus y squared, it's not x plus squared plus y squared, right? X plus y squared is what? X plus y times x plus y, right? Which equals what? X squared plus 2xy plus y squared. But why is this significant? Because this is 1, this is 2, and this is 1, which is exactly these numbers here. And then let's say I want to do, what's x plus y cubed? Well, that's x plus y times x plus y times x plus y. This becomes quite taxing, right? Eventually, as you get the numbers get bigger and bigger. And what comes out is that this is x cubed plus 3x squared y plus 3xy squared plus y cubed. And what are these numbers? These are the coefficients of the next row of the Pascal's triangle. So Pascal's triangle, the entries of the Pascal's triangle are the binomial coefficients, and they're called binomial because of this, because you can multiply binomials in a way, right? Cubed, squared, cubed to the 4th power to the 5th power, in a way that I don't have to actually FOIL things out anymore. There's a theorem to it. There's a connection between the coefficients of my terms and and Pascal's triangle. And it happens to deal with combinations. So there's a connection between Pascal's triangle, combinations, and multiplying binomials. That's like the three-headed combination. Okay. Okay. Now there's two more counting principles that I want to talk about. So one of them is I want to show you how to counting arrangements of objects that are repeated with repeats. So one typical problem that we deal with in counting is this idea of over counting. Sometimes we over count things, and we have to learn how to work with that. So I'll give you an example. Let's say I want to figure out, so an example here, find the number of arrangements that can be made with the word ladder. So I just want to figure out how many ways can I permute. This is a permutation problem. How many ways can I, because I care about the ordering, how many ways can I permute the letters in the word ladder? Or how, I should say, how many different ways can I do that, right? The problem is that there's 2 D's in them. So there's a repeat. So what we do here is we make believe that these D's are not the same. And what do I mean by that? Is consider LA, I'm gonna call this D, I'm gonna call it D sub 1, and I'm gonna call the next one D sub 2. And this is E, and this is R. So right now, the two D's are distinct. We make believe that they're distinct. We may believe. Now, in essence, how many different letters are there? Well, there's 1, 2, 3, 4, 5, 6. 6. I know there's 5 letters, L-A-D-E-R. I know there's only D is these two D's are the same. But I'm saying let's make believe that they aren't the same. Let's say that this is the first D, this is the second D. And then we made that distinction, so therefore they're not the same anymore for now. So if that's the case, then there's 6 different letters, right? And how many ways can we permute 6 things? Number of ways to permute 6 different letters. How many ways can I permute 6 letters? 6 factorial ways. That's right. I'm just multiplying 6 times 5 times 4 times 3 times 2. So then what is 6 factorial? 6 factorial is 720, right? So there's 720 ways to permute the letters in ladder. But we are over counting. Because now we have to switch. I know it's weird. We switch on to say that these are different, and then we switch off to say these are not different any longer. Because the word ladder, if I do ladder like this, D1, D2, right? If I were to permute it, L-A-D-D-E-R, in this number, I have this repeated twice in a way. So for every arrangement of letters, I'm counting it twice. Do you guys see that? So like if I have another arrangement, right? If I had like, I don't know, L-D-A-R-E-D, right? I just rearrange the letters of ladder. One of those arrangements, I have one D1 here and D2 here. And in the other arrangement, I have D-A-R-E-D. I also have this, but I have it switched. But in essence, these, if we forget about the distinction, right? These letters, these are the same. I just made this different so I can permute them and find a total number of ways of permuting 6 different things, but 2 of them are the same. So for every arrangement of letters, 2 of them are it's being counted twice in 720. If for every arrangement of letters, it's repeated twice, what should I do to get rid of that copy, to get rid of that double counting of that particular arrangement? I have to divide by 2. Do you guys see that? So this is the way to permute 6 letters, and this is the number of ways to permute 6 letters when 2 letters are repeated. So it's equal to 6 factorial over 2. I'm gonna write 2 factorial. So this is really what? 6 times 4, 6 times 5 times 4 times 3 times 2 over 2 factorial. 2 factorials cancel, so I'm just dividing 720 by 2, and I get 360 ways. Why do I divide by 2 factorial? Why am I stressing the factorial aspect? Is because for each arrangement of letters, if you want to rearrange the 2 D's, there's only 2 factorial ways to rearrange it because I only have 2 letters. So let me give you another example. Does anybody have any questions about this? No? Okay. Like, for example, what if I want to rearrange the letters of in cookbook? So what, so then look what we have here. We have two letters that are repeated, right? We have O's, there are four of them, and I have K's and there's two of them. So there's four O's and two K's. These are the repeats. So what am I going to do? I'm going to consider them. Oh, be careful, Mir. Be careful. Be careful. Not quite. Don't be careful with the 6 factorial underneath. There's something about that. But the a factorial is there, right? Because what we're going to do first is consider the O's all to be distinct. So I have the first O, the second O, the third O, and the fourth O. And then I have two K's. So I have the first K and the second K. So in essence, you can think of it as permuting 4 letters, right? Or 8 letters, sorry. So what's the total number of ways? Total number of ways to permute 6 letters. Sorry, 8 letters. Well, there's 8 letters to choose from, and arranging them, there's 8 factorial ways, right? Whatever that number is, we can write that later. But there's 8 factorial ways. Now, for every arrangement of letters, if I see all the O's, right, they're the same, right? If I do O1, O2, O3, O4 like this, it's the same thing if I do this, right? If I do the same thing if I do COOKBBBOOK. If I do this being a 2, this is being a 4, this is a 3, this is a 1, and then so on and so forth. How many ways is this? How many more ways are there? Well, I have 4 O's. So I have to so given this arrangement of the C's, the P's, and the O's and the K's, I have 4 factorial ways to arrange the O's. Do you guys see that? There's 4 factorial ways of arranging the O's. Arranging the O's. Or permuting the O's. I should write the word permuting. So do you see that? Yeah, Mir, that's better. That's better. So if I want to get rid of this repeatedness, there's this repeated nature of the O's, I have to divide 8 factorial by 4 factorial. I have to do that. So that's why I have to do 8 factorial divided by 4 factorial. So I can get rid of all the repetitive arrangement of letters with the 4 O's because they're all the same. But in this number, I'm treating them as different. So I'm considering the fact that they're different and then dividing out what's not different, what's the same. But then as well as in this number as well, there's the problem with the 2 K's. So for every arrangement, the K's are being repeated twice. The arrangement of using the 2 K's, they're repeated twice. So I have to divide it again by 2 or 2 factorial. So my real answer is the total number of ways to divide or to count the number of arrangements with the repeats is equal to 8 factorial over 2 factorial times 4 factorial. And if you do this, this is 8 times 7 times 6 times 5 times 4 factorial over 2 times 4 factorial 4 factorials cancel. And I'm left with 8 times 7 times 6 times 5 divided by 2. The 2 goes into the 8 4 times. And so I'm left with 4 times 7 times 6 times 5. And if I multiply them out, I get 840 ways. So there's 840 different ways to arrange the letters in the word cookbook. Okay, I'm glad that makes sense, John. So I want you just to start to see that when you have something that's repeated in the permutation, you divide to get that out, to get rid of that repeated example or arrangement, to get rid of the repeated arrangement, the overcounting problems. We divide, we don't subtract. Okay, so very quickly, how many ways can I rearrange? If you guys understand this, how many different ways can I rearrange the letters in the word MISSIPPI? How many ways are there? Hopefully it's not just you see the number of arrangements of letters. So how many letters are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So the top number here in the numerator would be 11 factorial, but what would be in the denominator? Right, so we have, right, Alexandra, we have 4 repeated S's, right? So we divided by 4 factorial. We have 4 repeated I's, so then we divide also by 4 factorial, and then we're left with 2 P's, right? And then we divide that by 2 factorial. So whatever that is, when you put it in your calculator or your computer yourself, which you can, it takes a little more cancellations, then that would be the total number of ways. Okay? Okay, I hope this was